postdoc through NLSI, working with both Bill and David Kring down at LPI. And Simone is going to be talking to us today about lunar small impactor populations over the last 3 billion years. And whenever you're ready, Simone.
Yeah, I'll thank you. And I'm going to do a sort of perhaps a weird talk today. I'm going to talk about the moon and the asteroids as well, and you will understand the reason why I decided to do that in a minute. So here, I'd like to get started just presenting some recent work that has been done by Michelle Kirchhoff et al. And basically, she measured the crater size frequency distribution of superposed craters to the floor of large lunar craters. And by large, I mean crater in the size range between 80 and 100 kilometers. And this has been done using the WAC mosaic at a resolution of 100 meters per pixel, more or less. And here is an example of one such crater, which is called Alcott. And then in these 4 panels, you see, for example, where you can actually see the crater size frequency distribution. And what is interesting here, if you look at the N1 values, N1 stands for the cumulative number of craters larger than 1 kilometer. You see that we are measuring terrain with a different crater density, which would imply a different age. And now what we did next is to apply the so-called model production function, which is basically a prediction on the number of crater, the density of crater as a function of time on the moon that has been derived by using the current near-Earth object flux coupled with the cratering scaling law. So you see the curves and how those curves fit with the data. And I would say that the fit generally is pretty good. And we use this information basically to constrain the age of those terrain, which can be seen here. So we are dealing with terrain which span from about 2 giga-years ago all the way back to 4 giga-years ago. So the bottom line of this, I would like to focus with is the fact that it seems to be, according to this data, that the shape of the impactor size frequency distribution had to be relatively constant in the last several giga-years. So this is a fact that we need to keep in mind. Next, we decide to extend this work by measuring even smaller craters, and this is possible thanks to the NAC mosaic. Here are a couple of examples. You can barely see probably the crater that we measure on this terrain because these are very tiny craters. Basically, we reach a sort of a resolution of about 40 meters or so, and therefore we could use this information again to derive an age for those units. And here is a couple of examples that I just showed you in the previous slides. We are talking about Jackson crater and Anaxagoras crater. The predicted age for those craters is of the order of 70 million years for Jackson, and the other one is of about 300 million years. And with the solid lines in this plot, you will see again the MPF fit of the data. So what this means is basically we are building an idea here that the shape of the impactor size frequency distribution on the moon has been really constant and in a time frame which goes from few tens of million years all the way back to several giga-years. Now, that may seem a little bit strange if you think about that. Now, we know that near-Earth objects basically are objects that are sort of leaked out the main belt. So the main belt is really the ultimate source for those objects. On the other hand, we know that in the main belt, there are a number of so-called dynamical families, which are basically breakup of large objects. Anytime you have a breakup in the main belt, you may expect to have some sort of variation in the impact flux over the moon. So how come that we see this steady shape for the impactor size frequency distribution on the moon, even if we see plenty of dynamical family in the main belt? So this is a major question we try to answer. And the best way to do that, I believe, is actually to go in the main belt and look at the small asteroids in the main belt. Here is where the talk turned a little bit, and I will start talking about the main belt asteroids for a while. Of course, we would like to observe those objects directly by surveys, but this is impossible so far. Here is a couple of examples. One of the deepest survey is SCAD, basically reached a resolution of 0.8 kilometer. And remember that we are dealing here with, we are interested in objects which range from about 1 meter to tens of meters, so, and perhaps hundreds of meters, but well below this limit that we have here. So possibly what we can do is use some sort of indirect measurement, and this is basically means trying to look small craters on the surface of main belt asteroids. That's the only way we have so far to address what is the real nature of the small main belt asteroids. And here is a little bit of a brief summary. I do not have time to go through the detail here. There's a bunch of asteroids that has been visited so far by spacecraft, and we are trying to use this data in order to make a prediction of the small main belt asteroid population. Well, it just happened that the best example so far is, without any doubt, the asteroid Vesta, because it is the largest object that has been observed so far in the main belt, and also because the surface of Vesta is terrain with a variety of ages, including very young ages, which is what we need in order to make a reliable predictions. And in particular, I'm going to talk about two interesting terrain which are related to the Sylvia Basin, which is a large basin in the southern hemisphere of Vesta, and Marcia crater, which is in the northern hemisphere of Vesta. So here we'll see the two terrain that we use. On the left hand, you have the portion of the ejecta blanket of Rhea Sylvia, and all the craters that we measured, really pushing the resolution of the image we have. I would just like to remind that those images have been acquired by Dawn, which orbited the asteroids for about 1 year, and the resolution of the image is about 20 meters per pixel. On the right hand, you have, perhaps you can barely see that, but you have a terrain which shows the crater that we measure on the floor, superposed to the floor of Marcia crater. Now, I want to show you the crater size frequency distribution that we obtain. So in violet, you have Marcia crater. In blue, you have the ejecta blankets of Rhea Sylvia. And in green are large craters that we previously measured on the floor of Rhea Sylvia itself. And the next thing is we can compare this with another asteroid, which is interesting, which is Gaspra, which is shown here in light blue. And in the solid curve, you will see the saturation level. So what this means, basically all this terrain that we are dealing with are well below the saturation. And this is an important point because we want to use the shape of the crater size frequency distribution to make reliable prediction on the population of main belt asteroids. So this is what we need to have. So those terrain are really great for our purposes. And in the next, you will find, again, best fit modeling derived in the framework of the model production that I briefly introduced you before. And on the left hand, you have basically a best fit of Rhea Sylvia crater counts. And I want to drive your attention on the fact, as I said, we do not have direct measurements on the size frequency distribution of small main belt asteroids. So clearly, what we do here is rely on a model which give us, the shape of the impactor size frequency distribution, even if we have no measurements. And the fact that we find a very nice fit, like the one that is shown here, indicates that those models are actually pretty good. And here, on the right hand, you have, again, a best fit of Marcia crater. So despite the fact that there is a great difference in crater density, or in age, if you will, we still find a good match with the data. So altogether, the data from Vesta and Gaspra suggest that the current shape of the shape that we see in the crater size frequency distribution has been relatively constant, even in the main belt, which is the source of the annuals, over a time span which goes from a few hundreds of million years all the way back to a couple of maybe 3 giga years. And here is, I'm trying to put everything together here. So, and the first point I want to make is that we did some recent measurements of very small craters on both the moon and the asteroids, and this provides a good match with the current annuals and main belt size frequency distribution as derived from modeling work. Therefore, this implies that the current dynamical and collisional evolution model from the main belt, and therefore for the NEOs, basically capture most of the physics that need to be taken into account, given that we find such a good fit. And finally, we can say now, safely, I would say, that we can use current NEO models in order to make reliable prediction on the age of a very young lunar terrain, which that has to be done using a very small crater. So this is something we can now say, I believe. And finally, I did not have time to go through this, which is a very important point to my mind. I just want to get the message out there. And the fact is the following: if you want to make age estimate on looking at small crater on the moon, then material properties like strength, density, and other stuff start to become important. You need to worry about the properties of the material if you want to make a reliable age estimate using small craters. And this is something we are now dealing and working on. And this is the end, basically, of the talk.
Great. Fantastic. Thank you, Simone. I know you've had some really great publications in the recent past. It's definitely great to see you working between two different teams within the NLSI. I had a quick question for you. You've been talking about main belt asteroids, and if we were to able to get out and start exploring some of these smaller main belt asteroids, would you expect them to yield any new information for you, or would they be saturated to the point that that they wouldn't be able to tell us anything because they're too small at that point?
Yeah, one of the problems with the small asteroids is, and I didn't have time to comment on this, but you are absolutely right. If you look at some of the small asteroids, they may be saturated, and we have indication that maybe this is the case for Ida and Matilda, for instance, that are relatively small asteroids. But on top of that, you have to take into account that it's easy to erase a crater of small objects. For instance, seismic shaking as triggered by large collision may actually move regularly on the surface, and therefore you may actually erase small craters. So it's risky to use small asteroids in this respect. That's why VESTA it's really helping us.
Yeah, great. I believe Sarah from Arizona State is. I believe Sarah from Arizona State is typing in some questions for you. If you could answer those in the general chat,